Okay, so in this section we're going to look at what's called the statistical relevance model of scientific explanation. In order to understand this model, you need to know what statistical relevance means, so let's look at that. For any population A and any properties C and B, C is statistically relevant to B if and only if the probability of B given A plus C is not the same as the probability of B given A alone. So consider an example. Let B stand for the theory that you have lung cancer, A stand for being human, and C stand for smoking. So this would say the probability that you have lung cancer given that you're a human and you smoke is not equal to the probability that you have lung cancer given that you are human. And if that condition is satisfied, then smoking is statistically relevant to lung cancer, which of course it is. So this is what this slogan means. It's just like, the probability of, say, having lung cancer given that you're human and you smoke isn't the same as the probability of having lung cancer given that you're human, which means smoking is statistically relevant to having lung cancer. Okay, here's another example. Suppose we sample 1,000 people and we find the following: that the probability of being pregnant given that you're male and you take birth control pills is identical with the probability of being pregnant given that you're a male. Well, since these two are identical, it means that taking birth control pills is not statistically relevant to getting pregnant in men. And that's good, right? That's as it should be, because it's not. By contrast, the probability of getting pregnant given that you're female and you take birth control pills is not identical to the probability of getting pregnant given that you're female, which means that taking birth control pills is statistically relevant to the probability of getting pregnant given that you're female. And basically what the statistical relevance model says is this. It says for any theory T and explanandum E, T explains E if and only if T is true, and T says some property that it's statistically relevant to E. So here's the idea. The theory that birth control pills prevent pregnancy doesn't explain why a male doesn't get pregnant, because his taking the pills is not statistically relevant to his getting pregnant. By contrast, the theory that a woman has taken birth control pills can explain why she doesn't get pregnant, since taking such pills is statistically relevant to her getting pregnant. So this, on its face, looks pretty plausible, right? If one property is statistically relevant to the other, it looks like you can explain the one by pointing to the other, explain why the one is present by pointing to the other. Well, what's the problem? The problem is that this model doesn't provide a sufficient condition for being an explanation, because the conditions of the model can be satisfied and yet you can fail to have an explanation. So here's a simple example. Suppose that a particularly ineffective birth control pill reduces the chances of pregnancy in females by 20%. And just so you know, you can make this number as low as you want. So we can just delete the 20 and make this 2%. Okay? So it reduces the probability of getting pregnant by 2%. And let's suppose that some other method reduces the chances of getting pregnant in females by almost 100%. Now, if Jane uses both methods and doesn't get pregnant, according to the statistical relevance model, we can say that Jane didn't get pregnant because she took the pills. Why? Because taking the pills is statistically relevant to getting pregnant, because the probability of getting pregnant given that you take the pills is 2% less than the probability of getting pregnant given that you don't take the pills. So it is statistically relevant. Those probabilities aren't identical, which means that you can explain the one by pointing to the other. You can explain not getting pregnant by pointing to the pills. But surely that's the wrong explanation. Instead, you should point to the more effective means of birth control as the cause of Jane not getting pregnant. Okay, this is kind of a contrived example. You might think, okay, sure, that's true in this case, but it's a weird example. It's not going to be true in many cases, because typically when one property is statistically relevant to another, you can actually explain the one by pointing to the other. I want to give you quickly the sense that that's just not so. So let's look at Tyler Vigen's website on spurious correlations. So what Vigen does is this. He takes huge sets of data from all different domains and then writes scripts to just try and find patterns, matching patterns in the data. So it's not like he starts out thinking that suicides by hanging, strangulation, and suffocation are going to correlate with US spending on science and space and technology between 2000 and 2009. He doesn't start out thinking that. Rather, he just runs a script that's looking for matching patterns of data, and this is one of the matching patterns that was found. So this is a really strong correlation. Okay, you would have a really low p-value here. But it's a spurious correlation. It's not interesting. It's just chance. It's just the result of the fact that if you look for patterns in enough sets of data, often enough, you're going to find some random chance overlaps, some random chance correlations. But notice that between 1999 and 2009, U.S. spending on space science and technology was statistically relevant to suicides by hanging, strangulation, and suffocation. So if you just relied on statistical relevance, you would say you could explain one by pointing to the other. But of course you can't, which shows that the model isn't sufficient. And again, this wouldn't be a big deal if this kind of thing happened infrequently, but it happens all the time. So we'll just look at a couple more. Number of people drowned by falling into a pool correlates with Nicolas Cage films between 1999 and 2009. Between 2000 and 2009, the number of people who died by becoming in their bed sheets correlated with per capita cheese consumption. And on and on and on. You can go to Viggen's website and see hundreds and hundreds of these things. He also has a nice little book where he sets these things out. Okay, so back to the slides here. The point is, the statistical relevance model does not offer a sufficient condition for being a scientific explanation because you can satisfy the conditions laid down by the model. That is, a theory can be true and statistically relevant to express a statistical relevance between two properties, and yet pointing to the presence of one property doesn't explain the presence of the other. Okay, the final model is the causal model, and we'll save that for the next segment.